Hi all, I welcome you all to the next lecture of Engineering Thermodynamics. So today basically I am going to discuss about absolute thermodynamic temperature scale, as well as we will see the Carnot Theorem and its corollary. And at the end of these two discussions we will go for some numerical applications of second law of thermodynamics. In the previous lecture we have covered the fundamental definitions of second law of thermodynamics. We have discussed two parallel statements of second law of thermodynamics. Also you have introduced about the heat engine, heat pump and refrigerator concepts. How do they actually work? And at the end of the previous lecture, we have also introduced the Carnot cycle, right? So today we will start our discussion with the topic called Carnot theorem. The study Carnot gave the two theorem basically based on the practical observations on his own proposed engine. So let's start our discussion with the Carnot theorem. So, what is basically a Carnot theorem? Carnot theorem states that no heat engine working in a cycle between two constant temperature reservoir can be more efficient than a reversible engine working between the same reservoirs. That means, in other words, we can say the performance of actual heat engine is not equal to the performance of a reversible heat engine. So it is given here. It means that the engine operating between a given constant temperature source and a given constant temperature sink. None has higher efficiency than a reversible engine. So reversible engine will have a maximum possible thermal efficiency, and reversible engine can only produce maximum possible work output. As we have seen in Carnot cycle, that is all the processes are reversible. So there is a reversible engine basically. So we were getting the 100% efficiency, but in the reality, in practical case, 100% efficiency is not possible. So if we prove this statement which is given there, none of the engine is higher efficient than a reversible engine. So consider this case. This is the picture which is given here. So if we consider the case, there are two heat engines, heat engine A and heat engine B. Assume that heat engine A is an ordinary heat engine B is a reversible heat engine, right? And both are operating between the same constant temperature heat source T1 and heat sink T2. The heat which is getting supplied to the heat engine A and B both are equal, that is Q. That means both are drawing same amount of heat from the source, and the heat rejected to the sink is Q minus WA in the case of heat engine A, and in the case of heat engine B it is Q minus WB. And because of these heat interactions they are generating some work, that is WA and WB. Now assume that we are reversing the direction. So we are reversing the direction. So direction of heat engine A, if we are doing so, right, the heat engine direction got reverse, and as well as this is a reversible heat engine, right? Reversible heat engine basically reverse the direction, but the actual heat engine cannot reverse its direction. So if you look at here, heat engine A is operating as it was operating earlier. It is drawing heat from the heat source T1 and rejecting to the heat sink T2. But this reversible basically heat engine B, it has changed its direction. When heat engine is going to reverse its direction, that means it is will be opposing, this is will be working like a opposite action, like it will be requiring some work. So it will be acting like a heat pump. So now it became the heat pump. Heat engine B became the heat pump, right? And it's drawing heat from low temperature sink and rejecting to the high temperature source, right, which is here T1, and is requiring work, and that work is getting supplied by the heat engine A, right? It is supplying that much amount of work which is required to run the heat engine B. But our assumption says that the actual heat engine is highly efficient compared to the reversible heat engine. So if my heat engine A is having more efficiency compared to the heat engine B, in that case the work output of heat engine A will be higher than the heat engine B. That means after supplying the requirement of work to the heat engine B, it will have excess work which can be used for as a work output. So if this is the case, the heat engine A has given the work to heat engine B, which is now working as a heat pump. This excess amount of work is coming out. So if we look at this combination of heat engine A and heat pump B, this together constitute a heat engine, right? If we combine these two, this will be acting like a heat engine, which is basically what it's doing. It is producing a net supply of work while exchanging heat only with one reservoir, that is heat sink T2. Basically, it's taking from here, and there is no contribution from the heat source T1. So because whatever is going from the heat pump here, Q is getting supplied to the heat engine heat engine A. So there is no contribution from this heat source. So this heat source can be removed. If it's going to be removed, in that case, this heat engine A and heat pump B combination will be forming a heat engine which is generating the mechanical work while exchanging heat with a single reservoir. In that case, it is going to violate the Kelvin-Planck statement. So any heat engine which is going to violate the Kelvin-Planck statement is impossible. It will be looking like a perpetual motion machine of second kind. So the assumption which we made earlier, the heat engine A is higher efficiency than a heat engine B, which is wrong. So from here we can prove that the none of the actual heat engine will have a higher efficiency compared to a reversible heat engine. So reversible heat engine will have highest possible efficiency compared to the actual engine. So this is a very simple thing. When we are there combined, they will be producing some work while exchanging heat with a single reservoir. So this became the PMM2. So now second corollary of Carnot theorem is all reversible heat engines operating between same two heat reservoirs must have the same efficiency. That means if two reversible heat engines are operating between same constant temperature source and constant temperature sink, both will have same efficiency. How to prove that? So let's consider two reversible engines R1 R2 are working between the same reservoir temperature T1 and T2, receiving same amount of heat from the source, right, that is high temperature reservoir. Let us assume that reversible heat engine 1 is more efficient compared to the reversible heat engine 2, right, and R2 that we consider. So lower efficient R2 is reversed to operate as a heat pump. If we are going to do so, as we are assumption is efficiency of heat engine 1 is greater than the efficiency of heat engine 2. In that case, the work output of reversible heat engine 1 will be greater than the work output of reversible heat engine 2. So this is the same case, right? Heat engine R1, heat engine R2, both are reversible now, and both are getting the equal amount of heat from the high temperature source and rejecting heat Q minus WR1 by engine 1 and Q minus WR2 by engine 2 and producing corresponding work WR1 and WR2. And our assumption is that the heat engine R1 is more efficient, or we can say the WR1 is greater than WR2. Now we are going to reverse the direction of one of the heat engines. So we are reversing the direction of heat engine R2. If we are going to do so, then heat engine R2 will be behaving like a heat pump. So if I am changing the direction of working of heat engine R2, it will be looking like this. Now it became the pump. So it's a pump means it will be requiring the WR2, which is getting supplied from the heat engine R1. So this is a heat pump now, right? So direction of heat interactions got changed, right? So it got changed, right? So whatever heat which is coming from here is getting supplied to here, right, to the heat engine R1. So whatever heat is getting rejected from the heat pump is directly coming to the heat engine. All right. As we have made an assumption that heat engine R1 is more efficient, that means work of R1 is greater than work of R2. So even after supplying the work required to run a heat pump, will have some excess work which can be utilized as a network output. So which is coming as WR1 minus WR2. So combination of these two, if you look at combination of these two, is going to create another heat engine, right? Heat engine R1 and heat pump R2 combined will be forming another heat engine, right, which is producing network output while exchanging heat with a single reservoir, that is T2, and there is no contribution of heat source T1 now, because whatever heat was coming from heat pump is getting supplied to the heat engine. So this also became the same combination combined system R1 R2 is producing work, and while exchanging heat with a single reservoir is going to violate the Calvin Planck statement. And the assumption which we made is now incorrect. That means all the reversible heat engine will have same efficiency when they are operating with the same constant source and constant temperature sink. Second corollary of Carnot is the efficiency of any reversible heat engine operating between two thermal reservoir does not depend on the nature of working fluid, and it depends only on the initial and final state of the system, or you can say it depends only on the temperature of the reservoir. So keep in mind, reversible heat engine performance does not depend on the properties of working fluid. It depends only on the initial and final temperature of the cycle, or you can say depends only on temperature of the reservoirs. So again, I will prove this by simple analogy which we followed earlier. So consider heat engine E and heat pump R working between the same thermal reservoir. Right, the efficiency is same because both are reversible engines and work on Carnot cycle. So we are going to prove for reversible heat engines, right? And we will prove that the performance of these engines do not depend on the properties of working fluid. So efficiency depends only upon the temperature of the reservoir. So work is produced by the engine E is equal to the work is required by the pump, because both are reversible, right? So one is pump, another engine. So look at here. So this is a heat engine, this is a heat pump. Basically, it's working like in reverse direction. All right. So whatever work is required to run the heat engine R is getting supplied from the heat engine E. All right. So if you look at just this combination, right, it's not violating any one of this law, because this is a heat engine, right? It is producing the same thing, and it is a heat pump which is requiring work and is getting supplied. So this is also not violating the Clausius statement. Now let's assume that I said this heat engine, right, basically heat engine E is more efficient. If I am saying is going to be more efficient, in that case what will happen? Even after supplying the work which is required to the heat pump R, it will have some excess work which can be taken out. If that is the case, in that case what will happen? Whatever heat which is coming from the heat pump is getting supplied to the heat engine, so there is no contribution of the heat source T1. So this can be eliminated in such a cases, right? Then this combination itself is going to form another heat engine, right, which is going to generate the mechanical work out of while exchanging heat with a single reservoir, right? So you look at this is a combination. Again, it became like a heat engine which is basically interacting with a single reservoir and producing the work, going to violate the PMM2, right? So same thing, so what basically we have not directly assumed like heat engine is more efficient. We said that by a working fluid, we changed the working fluid of heat engine so that the efficiency of reversible heat engine got increased, right? That is our assumption. Basically, we assumed like heat engine performance we have altered with the help of using highly volatile working fluid. So that is the case. In that case, heat engine is producing more work, right? If it is going to produce more work, then this combination is going to violate the PM means the second law of thermodynamics. That means it is impossible. So when our statement is going to be impossible, that means the performance of a reversible heat engine does not depend on the working nature of the working fluid. It depends only on the initial and final state or initial and final temperature of the cycle. All right, it's a very simple way you can prove that. Now, when we come to the efficiency of the reversible engine, the efficiency of a reversible heat engine depends only on the temperature. That is the case. So efficiency reversible is 1 minus Q2 by Q1, where Q2 is the heat rejected and Q1 is the heat supplied. That same equation can be written as 1 minus T2 by T1. So from here we can simply write this equation as T1 minus T2 by T1, that is called efficiency of a reversible heat engine. So similarly we can express the coefficient of performance of heat pump and refrigerator reversible. So we take the case coefficient of performance of refrigerator, which is nothing but Q2 divided by Q1 minus Q2, where Q2 is the lower temperature heat, right? Heat taken from the low temperature zone, and Q1 is the heat rejected to the high temperature zone. So this term is further can be written as 1 divided by Q1 by Q2 minus 1, because we have taken the Q2 out. So for reversible refrigerator, we can say Q1 by Q2 is equal to T1 by T2 because it depends only on the temperature. We substitute this value here. We can write coefficient of a refrigerator reversible is equal to T2 divided by T1 minus T2, or you can say that T low. This is the lowest possible temperature of the cycle. T low divided by T higher minus T lower. Right. This is known as coefficient of performance of a reversible refrigerator. If it is if somebody asks you find out the coefficient of performance of actual refrigerator, that will depend on the properties of working fluid, that is it, that need to be expressed in terms of u2. And if somebody is asking you to find out the coefficient of performance of reversible refrigerator, if it is a reversible, that means it depends only on the temperatures, right? So T2 divided by T1 minus T2. Similarly, you can find out for the coefficient of heat pump, where it will be T higher divided by T higher minus T lower, right? Don't get confused within these terms. Now come to the Clausius inequality. This states that if more than one thermal energy reservoirs are involved to get the net work output in a cycle heat engine, then for a reversible heat engine, the algebraic summation of dou q by T must be less than or equal to 0. Right. So let's suppose in an engine we are having more than 2 to 3 thermal energy reservoir through which energy interactions are taking place. Let's suppose it is taking heat from 2 reservoirs and sending heat to the one reservoir, or let's suppose it is taking heat from single reservoir and sending heat to the two different reservoirs. If you take the algebraic summation of heat transfer at and corresponding temperature dq by T, that should be less than or equal to 0, and this is known as Clausius inequality. If it is going to be greater than 0, that is impossible, and such kind of engine will be impossible. So as per the Clausius inequalities, algebraic summation and cycle dou q by T should be less than equal to 0. So when a system performs a reversible cycle, if it is a completely reversible, in that case summation of dou q by T will be 0, right? If it is cycle is not reversible, in that case it will be less than 0, but nowhere it will be greater than 0. If you are getting algebraic summation of dq by T greater than 0, that means such kind of device is impossible, right, as per the second law. Now come to the absolute thermodynamic temperature scale. Basically, so already I defined the temperature scale earlier. Again, I'm going to repeat that. So temperature scale, which is independent of the properties of substance, is called thermodynamic temperature scale. All right. So now, according to the Carnot theorem, the efficiency of a reversible engine is independent of the working substance. So we can say the efficiency of reversible engine is a function of only temperatures, right? T higher and T lower. So this is my equation number 1. All right. So where f is an arbitrary function of T higher and T lower, right, source and sink respectively. So we know that the efficiency of heat engine cycle, which receives heat Q1 amount of heat from source and Q2 rejected to the sink, we can express simply efficiency as a Q1 minus Q2 divided by Q1, which can be further rearranged into this way: 1 minus Q2 divided by Q1. So this 1 minus Q2 divided by Q1 is a function of basically temperatures, right? If we are talking about reversible heat engine, then so 1 minus Q2 by Q1 is a function of T higher and T lower, or in other way we can say Q1 by Q2 will is a another function of T higher and T lower. This is a new function, that is capital F, of T higher and T lower. So where F is a new function. So let us consider 3 reversible heat engines which are working in this way. So 2 reversible heat engines are working in a series, and another third heat engine is working independently between the given source and sink temperature. So there are 2 reversible heat engines, right, which are coupled in series between high temperature reservoir T1 and low temperature reservoir T3. So heat supplied to the reversible heat engine A is Q1, right, and heat rejected from the heat engine A, Q2, is getting supplied to the reversible heat engine B, and finally the reversible heat engine B is rejecting heat Q3 to the lowest temperature. And if you consider the reversible heat engine C, which is taking heat Q1 from the high temperature source T1 and rejecting Q3 to the low temperature reservoir T3 and producing work as WC, right, WC. So we can write the same equation, right, Q1 and Q2, Q1 by Q2 and Q2 by Q3, and finally Q1 by Q3 in terms of temperatures, right, as a function of temperature. So we can say Q1 by Q2 is a new function of T1 and T2, and Q2 by Q3 is a function of T2 and T3. Similarly, we can say Q1 by Q3 is a function of T1 and T3. right? Because they depends only on initial and final temperatures. So for heat engine A, temperature is T1 and T2. Heat engine B, it is T2 and T3. So we have written this way. Now Q1 by Q2 can be rearranged in this way: Q1 by Q3 divided by Q2 by Q3, and we know all these values. If we substitute these all values right here, right, we can get Q1 by Q2, which will be a function of T1 and T2, is equal to Q1 by Q3 is here. I have T1 T3, we can put it here. So from this equation we know that T3 is common, and this can be eliminated if we are going to define one more arbitrary function for T3, so that it is fixed for both the cases. If we do the careful observation of the above equation, left hand side T1 and T2, the value of right hand side will be independent of T3 if function has the following form. So this function is given. So function T1 and T3 can be written as another arbitrary function T1 divided by function T3, and T2 and T3 can be written as arbitrary function T2 and T3. So where this is an arbitrary function. So if we substitute this thing, right, these two equations over here, we can get a very simple term: Q1 by Q2 is some arbitrary function of T1 divided by arbitrary function of T2, right? This is an arbitrary function. The simplest way of defining this, arbitrary function is called absolute thermodynamic temperature, which is nothing but phi T is equal to T, which is proposed by the Lord Kelvin, and that's why we say sometimes this absolute thermodynamic temperature scale as Kelvin scale. So if we represent this arbitrary function T1 as just temperature, absolute temperature T, we can write Q1 by Q2 reversible depends on T1 and T2. So from here we came to know that the heat transfer between any two points along the scale will be the ratio of temperature at corresponding points. So Q1 by Q2 is equal to T1 by T2. So it was proposed by Kelvin, and absolute thermodynamic temperature scale is also known as Kelvin scale. All right. So we can represent now in terms of high temperature and low temperature, but in absolute thermodynamic temperature scale, the reference value is called triple point of water, which is a fixed value 273.16. So lower temperature is arbitrarily assigned as 273.16. This is not triple point of water. So we can say Q1 by Q2 is equal to T higher divided by T lower. If we substitute the value of T lower as 273.16, we can say T higher is equal to 273.16 times of Q1 by Q2. This is a simple relationship you get to find out the temperature at any location. So this is basically these three topics which were pending for the second law of thermodynamics. So we have closed. So now we'll see fastly two numerical problems. With that, we will close the discussion for today. So let's see the first problem, which says that an inventor claims to have developed an engine that takes in 105 megajoule at a temperature of 400 Kelvin and rejects 42 megajoule at a temperature of 200 Kelvin and delivers 15 kilowatt hour of mechanical work. Would you advise investing money to put this engine in the market? So what is basically has been given? He is basically claiming that his engine is taking only 105 megajoule of heat from a source at 400 Kelvin, rejecting 42 megajoule of heat to a sink of 200 Kelvin, and finally it's delivering around 15 kilowatt hour of mechanical work. So we need to propose whether that given engine will be good. It will be wise to invest money to purchase that engine. So let analyze that engine. So when we are analyzing this claim, we have to analyze with the help of ideal engine or reversible heat engine. So we can find out first the maximum possible efficiency. So maximum possible efficiency is the efficiency of reversible heat engine operating with the given source and sink. So maximum possible efficiency, we can find out efficiency max is equal to 1 minus T lower divided by T higher. Lower temperature is 200 and highest temperature is 400. We got the 50%. This is the maximum possible efficiency, right, if all the processes are reversible. Now let's see the claim of this fellow, which is saying, so now we can write efficiency thermal is equal to 1 minus Q2 by Q1. Q2 is the heat rejected and Q1 is the heat supplied, and both are given here. Heat rejected is given 42 megajoule and heat supplied is given 1.105 megajoule. If we are going by that, right, and we are going by that, we can find efficiency, right? So first of all, leave that. First of all, we see the what is the maximum possible, work that can be generated. We know the efficiency maximum. So the moment we know the efficiency maximum and we know the input heat also, we can get the maximum possible work output, which is coming around zero point 0.5 into 105, which is 52.5 megajoule, or we can say 14.58 kilowatt hour. So this is the maximum possible, work that can be generated if all the processes are reversible. But what this fellow is claiming, he is claiming that uh, it is able to generate 15 kilowatt hour of mechanical work. That means what? None of the engine will be more efficient than a reversible engine. So this claim basically is looking like a false statement, right? It's not going to be true, because none of the actual engine can deliver maximum work compared to a reversible engine. In reversible case, we are getting only 14.58, but he's claiming like 15 kilowatt hours. So his claim is wrong. So it will not be good to invest the money to purchase this engine, right? So his claim the engine can deliver more work than ideally possible, so I would not advise to investing money. So his claim is completely false. Now second one, if a refrigerator is used for heating purpose in winter, so that the atmosphere becomes the cold body and the room temperature to be a heated becomes hot body, how much heat would be available for heating for each kilowatt input to the driving motor? The coefficient of performance of refrigerator is 5 and the electromechanical efficiency of motor is 90%. How does this compare with the resistance heating? So this is the question. So solution, how to find out the things. So now refrigerator is working like a heat pump. So what desired effect is basically heating the room, right? So what all things are given? First of all, you look briefly. It is given like it is required. It is asking you how much heat would be available, right? What is the desired effect that heat is available for each kilowatt input to the driving motor. So work input is given 1 kilowatt, right? And for 1 kilowatt of input, how much heat it can be able to supply, while coefficient of performance of refrigerator is given 5. So coefficient of performance of heat pump will be one extra of this. So we can say coefficient of performance for heat pump is 5 plus 1, that is 6. So coefficient performance 6, we will find out how much heat it can supply. That is one thing. And another thing, the electromechanical efficiency of motor is given. So the work available, right, to be supplied will be calculated based on electromechanical efficiency. So coefficient of performance is nothing but desired effect divided by input. So coefficient of performance of refrigerator is coefficient of heat pump minus 1, or you can say coefficient of performance heat pump is coefficient of refrigerator plus 1. So coefficient of refrigerator is given 5, so we can say 6. This is the desired effect is heat, and this is the work input. So we can say that motor having 90% efficiency, so electrical energy available is W divided by 0.9. So you can say whatever input is given divided by the mechanical efficiency is the available energy. What is available energy? This is the available energy which is given here, W divided by 0.9. So if we are going to find out this will be nothing but H by 6. So H divided by 0.9 into 6. So we substitute the value, we can get 0.1852 times of heat, right? Direct heat. So it's asking how does this compare with the resistance heating. So we can say that the electrical energy, right, we can say basically the input is nothing but 18.52 percentage of the resistance heating, right? So whatever heat input is required to heat the room is nothing but 18.52 percentage of heat from the direct heating. All right. So somebody may ask you, what is this H? This H can be calculated because we know this electrical energy, which is nothing but W divided by 0.9, and W is 1 basically. So 1 kilowatt. So we can substitute the value and we can get the H. H will be calculated from here. So H is nothing but 100 divided by 18.52, right? 18.52. Why this 100 is coming? Because this is in percentage. So you need to divide by 100. So this 100 will go this side because the work is only 1 kilowatt, right? So 1 into 100, that will become 100, right? Divided by 18.52. So this is kilowatt. So we can get directly the heating as 5.3995 kilowatt. Take the next problem. With this, we are closing our discussion for today. A household refrigerator is maintained at a temperature of 2 degrees C every time the door is opened and warm material is placed inside, introducing an average of 420 kilojoule of heat, but making only a small change in temperature of the refrigerator. The door is opened 20 times a day and the refrigerator operates at 15% of ideal coefficient of performance. The cost of work is rate 2.50 per kilowatt hour. What is the monthly bill for the refrigerator? The atmosphere is at 30 degrees Celsius. So keep in mind, lowest temperature is 2 degree and highest temperature 30 degrees. Between that your refrigerator is working, and heat that need to be removed, right? Heat leaked into the freezer is given here, introducing 2420 kilojoule every time you are opening that, 20 time we are opening the door. So 20 multiplied by this much is the heat that need to be removed, that got leaked inside the refrigerator, that need to be removed, right? And it is clearly said that the actual performance is 15% of ideal performance. So this is the refrigerator, this is the lowest temperature, this highest temperature, and this is the work input. So ideal coefficient of performance depends on the temperatures, right? T lower divided by T higher minus T lower. So T lower is 275 and T higher and minus T lower is 28 degree. So you divide that, we get this ideal coefficient of performance, but actually is 15% of it. So actual coefficient of performance is 0.15 times of coefficient of performance ideal, is coming as 1.4732. So we have to use this and to find out the monthly bill. So hence heat to be removed is nothing but 420 into 20 times we are opening. So total this much heat to be removed. What is this heat? This heat is to be removed from this cooler space, that is freezer. So this Q2 is this one, and we need to find out the work input. We know the coefficient of performance, we can substitute the values. So work input, work required can be calculated directly by using this coefficient of performance is equal to Q2 divided by W. So W is equal to Q2 divided by this term, right? That will give us this one, kilojoule per hour, kilojoule per day, and that can be converted into kilowatt hour by dividing by 60, right? So we can get this one 1.5835 kilowatt hour per day. So monthly bill is 2.50 per kilowatt hour. So we can multiply by 2.5 into for 30 days, right? This is for one day. So 30 days we can get 118.2 rate as a monthly bill, right? So I'm closing discussion here with this problem. Try some more numerical problems from the book, right? If you are having any doubt in this concept, please feel free to contact me at any time. So thanks for your patience. All right, have a nice day. Good day.